Okay, so today we're looking at still summarising numerical data. So we were doing that with box plots, and we're still looking at numerical data. But now we're going to start looking at the mean and the standard deviation. So just remember, the mean is the X with the line above in your calculator, and standard deviation is written as SX in your calculator. So when you go through all your stats, you can see that happening. So we know that the mean is the average, so that's another thing. So where you add up all the data and divide by the total values. So as we saw earlier on with the box plots, and when we were talking about the median, we said the median was better when the data was skewed or if there was outliers, because those extremes can affect the mean. So when do we only really we only use the mean and the standard deviation when we have symmetric data. Okay, so that we only use it because these two things will be affected by extreme values or skewed data. It won't be a true representation of our middle point, okay? So when we have symmetric data. So when we see symmetric data, we'll see a bell shape, or if with the box plot, we'll see even boxes in the middle there, and so on. So you all know that. So, okay, so we saw that the measures of centre, we had two types. So we've got the median, and as I said, it's a resistant statistic, not affected by outliers. So it's better use for in skewed data, and the same with the Q1 and Q3. So down here where we're starting to talk about the mean, we can see that it's for symmetric distributions. So when we talk about the centre for symmetric, you can use the median and you can use the mean. It doesn't matter either way for symmetric data. But we'll often find we're using the mean, and we'll see, because we're going to use these other rules as well. Okay, so this is the formula for standard deviation written down here. By no means do you ever use it to calculate the standard deviation. So remember, the standard deviation is just when you've got your lists and you get all your data and all that, when you do your stats calculations, you just get it there. We just pop this in so that you have, this is how they find it out. And so that you can see, because when you find standard deviation, can you see how in the formula it has the mean in there? So if we have extreme values, it's going to affect this as well, isn't it? Because it uses the mean to find it. So it's to show you that years ago they used to ask, what does the formula look like? So you would need it in your thing. I haven't seen anything like that for years, but it's there just in case, okay? All right, so we're going to talk about, you'll see they'll say a normal distribution. Normal distribution means that it's symmetric, okay? Another way to say we have symmetric data, okay? You'll often see these words in the question, the data distributions that are approximately bell-shaped. So, because symmetric data looks like a bell, yeah? Or you'll see that it's normal, has a normal distribution. So if you see the word normal distribution, it means it's symmetric. Okay, so they've put a few little examples of what symmetric can look like, and there it is. So what we're going to look at today, there is this rule called the 68, 95, 99.7 rule. What was it? 97.9. So we're going to look at this rule that you use for normally distributed data or symmetric data, and it's called the 68, 95, 99.7% rule. Okay, so only can be used when you have this beautiful bell shape here like this. So what happens is when you have the bell shape here, whatever value's sitting right in the middle there, that will be your mean value. Okay, so say for example, I said I was talking about, I don't know, the average weight of our year 7 class or something. So I'd say their mean is, I'm going to just say 50 kilograms. Okay, now I'm just also going to tell you down here, I will tell you this. I'm going to say that their standard deviation is 2 kilograms. All right, I'm making this up. Okay, but just to show you. So what happens is you can see we can break up this bell curve in terms of standard deviations. So if I go 1 standard deviation above the mean, so I'd add +1 in standard deviation. So if we were talking about our example here, this would be 52 there, okay? And we could also go up +2 standard deviations, and that would take me to 54, yeah? And if I went up 3 standard deviations, I would be up at 56, okay? This is an example along here. Okay, then you can also go down underneath the mean. So if I go -1 standard deviation, I would be on 48. Yeah, if I went down 2 standard deviations, I would be at 46. And if I went down 3 standard deviations, I would be at 44. Okay. So what you can do with this rule is you can work out where the percentage of data was. So say in our example, we were measured 100 kids. You know, I'm doing it nice and easy. 100 kids. So what we can say, when you are +1 and -1 standard deviation. So when I am in here, so -1 and +1. So between 48 and 52, see how it's 34 and 34? That's 68%, yeah? That 68% lie between -1 and +1 standard deviations. So in my example, I could say 68 kids were in the weight range of 48 to 52. Can you see that? Because I said there was 100 kids. So I'm doing it nice and easy for you so you can see. Yeah? Now, if you go, if I went 2 standard deviations, so 2 below and 2 above, in there is 95% of the data. So in my little example here, because I had 100 kids, I'd say 95 of the kids, 95 kids lie between 46 and 54 kilos. Okay? So, and then you can see if we did 3 standard deviations plus, above or minus the mean. So in here, along that whole big one up there will be 99.7. Now, can you see 99.7 is very close to 100%? Would you agree? Yeah. So they sometimes will call on that fact. So you might need to write a little note down that between plus and minus 3 standard deviations is approximately all the data. Yeah? So if you think about it, I'm going to say roughly between 44 kilos and 56 kilos we find all these kids. There will be a few out, but most of them. So if they ever say you can work out standard deviation, you can find standard deviation approximately, by going the range divided by 6. Can you see why I'd say 6? Because we break it up into 1, 2, 3, 4, 5, 6. Can you see that? It's 6 equal sections, isn't it? So say this range, say I said the maximum was 56 minus the minimum, which is 44. So what's 56 minus 44? That is 12. And then if I divide it by 6, so what's 12 divided by 6? I get 2. That's the standard deviation, isn't it? Yes? So you can, if you're ever asked to roughly estimate the standard deviation, you can say well, it's roughly the range divided by 6. Okay? We can ask a few other little questions. We could say for example, what is the top, if you look, the top 16%. Can you see if I go this way, that's 16%, yeah? So I could say in my little example, if you weigh more than 52 kilos, you're in the top 16% of the weight range for this class. Can you understand that? Yeah? So we can use, what would you be if you're in the bottom 16%? You'd be less than? 48. Yeah, good. 48. That's right. If you're in the bottom 16%. So can you see they can ask lots of little questions around this ruling, and you're going to have to practice it to get used to it. So if I look here at these diagrams here, you can see I've done up here, this is when you have just one. It's to help you learn the pockets. So you can see here, there's 16% when you're one standard deviation above and minus. When you are 2, so you can see here, I don't know if you can see, when you're 2 standard deviations, plus or minus, these little tails end up being 2.5%. So if I went back to our example, I think you can say you're in the top 2.5% if you weigh more than whatever. And then down the bottom, this last one, if you are 3 plus or minus 3, these tails are tiny, they're very little, and you're actually, because you've only got 0.3%, this guy is actually less than 1%, way less than 1%. So it's 0.15% of the data lie between that. So if I've got 100 people, you've pretty much got 0 out there because you round, okay? So you're going to get used to this. So let's do a couple of questions so you can see what I'm talking about. Okay, so you're going to see this written like this in your exams and your tests. Lizards in a reptile house are given cricket nymphs to eat at feeding time. The length of the cricket nymphs are approximately normally distributed. Once you see those words, that should trigger to you are allowed now to use the 68, 95, 99.7 rule. Okay? They will have to state it. So as soon as you see that, you are doing that. And surprise, surprise, you get given the mean. So look out for that. So now I can say, all right, good, the mean is 12.7, and they're probably going to tell me standard deviation. Yep. So standard deviation is 2.3. So if you, what I suggest you do is straight away you should be just draw a little bell shape and pop your numbers in there. So the mean's at 12.7. If you go up 1, 2, 3, or you could go down 1, 2, 3 standard deviations, just work out the number. So if I have 12.7 and I add 2.3, what do I get? I get 15, don't I? Yeah? And then if I add another 2.3, I get 17.3. And if I add another 2.3, I'd get 19.6. Is that true? Yeah? And then you can go minus. So if I go 12.7 minus 2.3, I would get 10.4. Yes? Minus another 2.3, I'd get 8.1. And minus another 2.3, I'd get 5.4. 8. Is that correct? Checking my maths. 6. Yes? 5.8. Okay, so now it'll make you easier to do the question. So let's have a look. The percentage of crickets, so I just need the percentage of crickets, nymphs who are expected to be longer than 15. So I go up here, 15's at 1. If you go back to your diagrams, what was the percentage if it was 1 plus out this way?
16%.
Yeah, so 16% will be longer because that's bigger, yeah? So we just have to write 16%. Okay, the percentage, the next one, the percentage of crickets nymphs expected to have a length between 8.1 and 15. So if you go here, I've gone down 2 and I've gone up to 1, okay? So what you might do is go back to that original diagram where they're all broken up and look at the pockets. So remember we had 34 here, 34 here. What was this little one in there? I'm talking about, I'm going to pause. Okay, so I'm talking about this diagram. Can you see we've got this percentage because we've gone down there. Then I've got this one and this one. So I've got 68 plus 13.5. So what's that going to be? So what I'm adding is the 34 plus the 34 plus the 13.5, which equals, okay, so we get 81.5% are between those two numbers. All right, so use this guy to work out those ones. Then we've got the number of cricket nymphs expect. Now, be careful. Once we see the number, remember we want a number. So we may use our percentage. Now, and now you can see if we have to use it, they're going to tell us how many we've got. So the number of nymphs expected to be shorter than 10.4 millimeters. So if I go 10.4, that's 1. So what's shorter than that? What was that little pocket? Wasn't it 16%? Yeah? So I'm going to say 16% of the population are less than that. So they want the number. So I'm going to say 16% of the 850. So that can change to 0.16 times 850. And what do we get? At 136, we get the nymphs, that number of cricket nymphs. Okay.